Welcome to homework.
Question number 21 wants us to find the orbital periods of two objects in our galaxy. One is a star 5,000 light-years from the galactic center, and the other is a globular cluster at 50,000 light-years from the galactic center. To solve this problem, we're going to need to use this expression here, a modified version of Kepler's third law, which states that a cubed is equal to m1 plus m2 times p squared. Now a is going to be the distance of these objects from the galactic center, and we'll have two values for it. We'll call the distance of the star a sub 1, that's 5,000 light-years, and a2 will be the distance of the globular cluster, 50,000 light-years. Now both these distances are in light-years, but in order for them to work in our formula, we need to have them in astronomical units. So we'll need to do a bit of unit conversion here. Let's start with A1, the distance between the star and the galactic center. It lies at a distance of 5,000 light-years from the center of the galaxy, and to convert this to astronomical units, we'll first need to multiply by 9.46 times 10 to the 15 meters. That's how many meters there are in 1 light-year. And then multiply by 1 astronomical unit over 1.5 times 10 to the 11 meters, the number of meters there are in an astronomical unit. So now we can cancel out the light years and the meters, and the distance of this star from the center of our galaxy turns out to be 3.15 times 10 to the 8 astronomical units. Now let's perform the same calculation for our globular cluster, which lies at 50,000 light-years from the galactic center. Once again, we need to multiply this by 9.46 times 10 to the 15 meters over 1 light-year, and then multiply again by 1 astronomical unit over 1.5 times 10 to the 11 meters. Once we make the necessary cancellations, we can again get the distance in astronomical units. It turns out that this globular cluster lies at 3.15 times 10 to the 9 AU from the galaxy's center. Now that we have all the appropriate units for use in our formula, let's go ahead and rewrite it so that we're solving for p squared. That will be equal to a cubed over m1 plus m2. Now, m1 and m2 are the masses involved in this problem. One of them is the mass of the galaxy, which compared to the mass of the star and the mass of the globular cluster is much, much larger. So if we call the mass of the galaxy m sub 1, we can essentially say that it's approximately equal to m sub 1 plus m sub 2, meaning the mass of the star and the mass of the globular cluster here will be negligible. So, since we need only worry about one of the masses for this problem, let's go ahead and solve for the orbital periods here. First will be the orbital period of the star. That will be p sub 1 squared, and it'll be equal to 3.15 times 10 to the 8 astronomical units cubed, divided by the mass of the galaxy, which we actually found in a previous problem, to be equal to 8.7 times 10 to the 10 solar masses. Dividing that out, we find that p sub 1 squared is equal to 3.59 times 10 to the 14 years squared. Now, that's p sub 1 squared. To find the actual value of p sub 1, we need to take the square root of both sides. When we do that, we find that the star has an orbital period about the galactic center equal to 1.9 times 10 to the 7 years. Alright, next we need to find the orbital period of the globular cluster. P sub 2 squared will be equal to 3.15 times 10 to the 9 astronomical units cubed divided by 8.7 times 10 to the 10 solar masses. When we divide that out, we find that P sub 2 squared has a value of 3.59 times 10 to the 17 years squared. Once again, we'll need to take the square root of both sides to find the value for P sub 2. It turns out the globular cluster has an orbital period of 5.99 times 10 to the 8 years. The second half of this question asks, if this star, the Sun, and the globular cluster were lined up on the same side of the galaxy, where would they be relative to each other after one galactic year? Let's just draw out the orbits of these three bodies. The outermost orbit will be that of the globular cluster. The next one in is our Sun. And finally, the closest to the galactic center is the little star at 5,000 light years from the galactic center. And now I'll just draw each one as three different colored points in their orbits. The globular cluster will be blue, the Sun is green, and the star will be red. Now, one galactic year denotes the time it takes the Sun to orbit the galactic center once. We'll call that P solar, and that is equal to 2.25 times 10 to the 8 years. Now, the way we're going to determine each object's position relative to one another after one galactic year is to determine the number of orbits the globular cluster and the other star make when the Sun completes one orbit. To find the number of orbits made by the globular cluster, GC, after one galactic year, we can just take the galactic year and divide it by the globular cluster's orbital period. So we'll have 2.25 times 10 to the 8 years divided by 5.99 times 10 to the 8 years. When we divide that out, we find that the globular cluster completes about 38% of an orbit by the time the Sun has completed one orbit about the galactic center. Now, we just need to make the same calculation for the star. We can just take 2.25 times 10 to the 8 years and divide by the star's orbital period of 1.9 times 10 to the 7 years. When we divide that out, we find that in the time it's taken the Sun to complete one orbit, the star inward of it has completed almost 12 orbits, so about 11.8 orbits of the galactic center. Now let's mark the positions on this orbital diagram of each of these objects after one galactic year. The little star will be kind of almost at the 1 o'clock position here. Then the globular cluster in the outermost orbit will be down here at about the 8 o'clock position. And since the Sun has completed one orbit of the galaxy, it'll be at the same position after one galactic year.